Welcome. Sorry, no Kahoot first thing. We'll get one later, don't worry. Don't panic. A big sigh of relief there. Oh, thank goodness for that. Okay, so today I'm going to talk about something which connects backwards to the previous lecture because it will provide us with further example of recursive data types. But maybe importantly, it also connects forward to courses you will do in the future, not about functional programming, but about algorithms and data structures. So the focus today is really to do with finding efficient ways to represent data. And this is a fairly big topic. As I say, you will do one or two or maybe more courses specifically about that topic. How to design data structures and algorithms for working over data structures for efficient computation. So these are very fundamental things. Today we're going to get a little taste of that. And in the process, we're going to learn a little bit about those concepts, but also exercise our recursive data types. So data structures, data types, they all kind of sound similar and they all blur together. The distinction I want to make here is a data type in some sense is something really concrete. We're building a model of something we want to represent in our program, like the hand of cards, like the cards built from ranks and suits and so on. A data structure can be thought of maybe a little bit more abstractly as a particular way of storing data and a particular collection of operations that you would like to perform on data. And it's somewhat independent of the way that we actually model the data in the programming language. So the choices here on how we store data are going to be influenced by what we want to do with data. And the influence we want that to have is to make choices in our design of the storage of data so that operations that we will commonly perform on that data will be efficient. Now, the slide says that we're going to look at two examples, queues and tables. I'm just going to look at one example in the lecture, but I have recorded a small video for the other example if you're interested in that one. So the other example doesn't involve recursive data types, whereas the example of tables will. So what do I mean by a table? Well, something we've talked about before. A table is a way of representing the association between two kinds of information. The information here in this table on the left, these are called the keys. And for each key, there is a corresponding value. So in this particular table, this is representing telephone numbers, internal telephone numbers. For every key, which here is a string, there is an associated value, which here is an int, let's say. So that might be a representation of a phone book. So this is a visual representation of that structure. But we're going to talk about computer representations, or more specifically, Haskell representations. Now, when we think about representations, there are a number of things that come in. One of them is convenience. Convenience to you as a programmer. If we want to represent a small table, like this one here, one convenient way to do that is to use the data types that are already existing in Haskell. In particular, we can use a list. A list containing pairs of a string and an int. So we have all the types we need to represent this structure. But what we'll see is that that maybe isn't the most efficient representation if we want to represent really large tables. So the way that we would represent it using the Haskell we've seen so far is to represent a table using a list. So we can make a type synonym and say a table for some key type k, could be string, it could be something else, and type some value type v, it could be int, but it could be something else. So whenever I write table kv, what I mean is a list of pairs of keys and values, a list of key value pairs. And here's a little example over here. This is a possible value of type table string int. It represents the table by pairing the key x and a value which is an int. Okay? Any questions about that? We've done this before. We've used tables represented as lists earlier in the course. And one of the reasons we did it is because we can reuse a standard function called lookup. So lookup, if you give it a key and a table, or key value pairs, it will tell you which value that key corresponds to. So if I'm looking up in the phone book, this key, I would like to get this value back. Now, unfortunately, for every key, there might not be a value. There might be a key which doesn't have a value, a string which doesn't have an entry in the table. So, of course, you could, for a function lookup, give an error. But that's not always so convenient to program with, because you're never sure whether there's a value in the table or not. And so the natural choice then is to represent the type of the result as a maybe. You maybe get a value back. So if the value is in the table, you get just of that value. But if you look up something that's not in the table, you get nothing. Any questions about this? We've seen it all before, but it's a refresher. Now you might ask, well, what's this junk on the front here? What's all that to do with? So this is a function that takes two arguments, a key and a table, and maybe gives you a value. And this bit of extra information says, well, this doesn't work for any old type of keys at all. There is one crucial property you need for your type of keys. If you're going to look up a key in a table, then you need to be able to test whether the key you're looking for and the key in the table are the same. And to do that, you need to have an equality operation. Okay? So this is just the type class constraint that says this works for every type which is in the EQ class. In other words, every type which has an equality comparison operation. Okay? So the question is then, how long does it take to look up a name in a table? Well, that depends on the representation of a table. We've chosen a list as our representation. So let's suppose we have a table with n entries, n rows in our table. Now, if the name is in the table, on average, if the table is organized in a fairly random fashion, and if we're asking for fairly random keys, then we expect on average to take n over 2 steps to find the value for a given key. And if the key is not in the table, well, then we'll have to look at every element in the table before we just concluded that we can find nothing. So we either take n over 2 if it's in there, or we take n steps when it's not in there. So overall, something between an average n and n over 2. Depends on your distribution of data. But those constants don't matter. Point is that as your table gets bigger, it grows linearly. So if we have, say, 1 million elements in the table, then we're going to sort of the order of 1 million computation steps or 1 million comparison operations on average to find the thing we're looking for. Okay? It might be a bit less, it might be as much as 1 million, but it won't be significantly more. And when we want to say roughly, we use something called big O notation, and it has a more precise and more general mathematical definition. I'm not going to give it to you, I'm just going to give you the intuition. Basically, we say that this problem of looking up a name in a table represented as a list takes order n steps. That means it grows linearly with n. Now, it might be 2n, 5n, 5n plus some other constant. Those constants are not interesting. The big picture is it takes the order of n steps. Okay? Sometimes referred to the complexity of the problem, the time complexity. Okay? So any questions? Now, is that a problem? Is 1 million elements a problem? Well, not really. We can represent 1 million elements. We can search in it. It might take a little while, but if we have to do it often with a large number, this will actually slow down our programs significantly. So can we do better than that? Can we organize our data, even without knowing what the data is, being able to write functions that work with any kinds of data, not just strings or numbers, but anything where we can compare elements? Can we do it in a more efficient way? So imagine you've got a table here, and these blank lines just mean I haven't bothered to draw in. There's a number of rows here. I've just drawn in the first entry in the table, the key of the first entry, the key of somewhere in the middle, and the key at the end. So imagine you have a phone book, okay? Big, thick book. Actually, you probably don't know what a phone book is. They used to actually have books printed with all the phone numbers of the people in a country in one book, maybe several volumes. Sweden, maybe it wasn't so thick. It was maybe so thick. In the UK, I think maybe it was 3 or 4 volumes. It's called a phone book, right? Now imagine you are looking up a name in the phone. You wanted to look up Kuhn Claassen in the phone book. So our previous data structure, the way that we find something in a list, that we only have one way we can do it. We have to start at the beginning of the list and work our way through. Because that's the way lists are built. They're built by adding elements on the front of other lists. So whenever you want to take a list apart, you do it one element at a time at the front of the list. So what that corresponds to, if you have your phone book, is that you start on page 1, column 1, and you look, is the first entry in the phone book Claassen? No. You move to the next entry. And when you finish the first page, you move to the next page. Is the first entry Claassen? No. Okay? Clearly, that's going to take a very long time. It's a stupid strategy. That's the strategy that our list representation is doing, because it forces us to work through the list from the beginning to the end. We might get lucky. We might be looking for Mr. Arbonen. I don't know what that name is. We might be looking for that person, Alfred Aardvark. Great. And then we find it quickly. But most of the time, we're going to do really badly. Okay? Now, a more reasonable strategy, even if you don't know anything about the alphabet and the distribution of names, we know quite a lot about the distributions of names, so we can make quite good guesses in a phone book where something might be. But we're going to look for a general method that works with all kinds of data with unknown properties. But one thing is for sure is we don't need to start in the beginning. We can start in the middle. But why is that? It's because the data is arranged alphabetically. If we start in the middle and we're looking for a C, and the entries in the middle start with an F, then we know we'd have to look in the left hand in the first half of the phone book. Whereas if it comes after F, we look in the second half of the phone book. So at each step, we can roughly divide the problem size in half, right? Now that works assuming that the table can be sorted arranged in order. Okay, so that's important. We need to be able to arrange the table in order. So that means that we will have a method that works not just when we can compare things for equality, but also when we can compare things with an ordering relation. Okay? So we're going to rely on that fact. So many things that have an equality also can be compared with an ordering relation. Is one thing less than another? Is one string less than another? Well, if it's an alphabetical word, it means does it come earlier in the dictionary? So let's build a representation of this data structure that makes it easier to perform this operation, namely to start roughly in the middle and break our problem down into either searching in the top half or the bottom half. So we take that data, that table, and let's split it into the first half, the first half of the table, the bit in the middle, the entry in the middle, and the second half of the table. So let's define that as a data type. Let's represent this thing here as a data type. It's a table of keys and values. And what is it? How do we build that thing? Well, it's three components which are joined together. It's a table, that's this one up here. It's a key here and its value, which I've not written in here. And it's another table. So there's four things, in fact, not three things, but four things. A table, a key, a value, and another table. So a table is going to be the join of a table of the same kind, a key, a value, and another table. So I've defined a recursive data type to represent this table. Because that means that not only are we going to split this big table into a first table, the entry, and a second table, we're going to do that recursively. We're going to also split this one into its middle element, the ones that come before and the ones that come after. Okay? Now that doesn't quite work. So I'll come back to the data type. That doesn't quite work. But before I do that, let's get a picture that doesn't involve any Haskell. Let's get a picture. Let's get an idea for this just with pictures. So we know that we can draw recursive data types as tree structures. We can draw them as trees. So let's draw this as a tree. So here's an example of a table represented as a tree. The three components, so it starts here. So this is the entry, as it were, in the middle of the table. All the things on this side are the things which come before this one in the table, and all the things over here are the things that come after this one in the table. Okay? So this is the things before to the left and the things after to the right. So what do you notice about this table is everything that comes before this one in the table has a key which is smaller than this key. And what do I mean by smaller? Well, in this case, they're strings, so it means they come earlier in the dictionary or in the phone book. So C comes before N, and A comes before C. And so that's respected here. Everything in this left table comes before N, and everything in this right table comes after N. And not only that, but you can view these guys, this one down here and this one over here, as little tables, smaller tables. And the same property holds in this table. Everything before R in this table is on the left, and everything after R, and that should be an not an O, comes in the right-hand table. Okay, questions? Okay, so representing tables as recursive data types, that's great. But what's wrong with this recursive data type? There's something wrong with it. Yeah?
There is no base case.
There's no base case. This only allows us to build infinitely big tables. Okay? We can do that in Haskell, that's cool. But it's not really what we're looking for. We're not looking for infinitely big tables. We need a base case. So what is the base case for a table? Empty. Yes, an empty table. Okay? Sometimes a table is empty. Just like sometimes a list is empty. The base case for lists is an empty list. The base case for tables is an empty table. So we need a constructor to represent an empty table. For the data type of expressions that we used in the previous lectures, and you're using in the lab, what's the base case for that recursive data type? The empty expression? No. What was it? It was a number. It was our representation of a single number, a num. Okay. So what do we do when we want to look up a key in a table? What are the operations that we perform? Well, here I've listed them, and that's sort of a bit dry. So let me look at it on the picture. So here's a key. I want to look up this key in this table. Now, where do I start? Well, I have to always start at the root of the table. That's like with lists. You always have to start at the beginning of a list. You can't jump into the middle of a list. We can't jump into the middle of a table. We always start at the root of the table. And in our representation, the root is the sort of middle point. Okay? So what do? Well, we compare the key we have, the key we're looking for, with the key in the table. And they're not equal, okay? If they were equal, we would have found what we're looking for. But in this case, they're not equal. So where do we look next? Well, we have to ask the question, does this key come before this key or after this key in the dictionary ordering? Well, P comes after N. So it means that we're going to search for this key in this right-hand subtree. Okay? So we can ignore the rest, and we can now go down recursively and compare, look for this key in this tree here. And we begin again at the root of the tree. We compare with Runeson, and we say, is it bigger or smaller, or is it equal? It's not equal, but it is smaller. So we go to the left, and now we have this smaller tree, and now when we compare, we find it, and so the answer will be just this thing here. Now, if we got to the end of the tree and we didn't find it, if we got to an empty table, then the answer would be nothing. We haven't found what we're looking for. Okay? Now, in these pictures, I've not drawn in the empty tables, but really, at every leaf in this tree, you can think of there's two subtrees, both of them which have empty tables. Okay? So there's invisible leaves down here. That's the way my Haskell representation is going to represent this tree. Any questions? Okay. So let's just refresh ourselves then what we're going to do to define looking up a key in a table. If the table's empty, the key's not found. Otherwise, you compare the key with the key in the middle of the table, so to speak, roughly speaking. And if they're equal, we've found the value. If the key's less than the key in the middle, we look in the first half of the table, the left-hand subtree. Otherwise, we look in the second half. So let's look at a little bit of code to do that. So here's a bit of Haskell. We've defined the table data type, as we described, recursively. It looks a little bit complicated, this data type, and that's just because we're making a data type that works not with a specific type of key and a specific type of value. We've made it polymorphic. It will work for any type of keys but we'll need to be able to compare them, and any type of values. So these extra K and V, this is the type of keys and the type of values. So for every type of keys and type of values, this defines a new data type. And then when we use the recursion, we have to remember to pass these types along, these type parameters. So that's what makes this look a little bit more complicated than some of the earlier examples. So let's define the lookup function. So the lookup function, you're looking for a key in a table, and the type of the keys and the type of the keys in the table are the same. That's good news. And we maybe get a value back. Now, in order to be able to do this operation, we have to be able to compare the key that we have with the keys in the table using the comparison operators. Is it equal to? Is it less than? Is it greater than? So the only types where you can do that are types which are in the OR class. And that's what this bit on the front is. So let's define this. And we define it by equations. And we can define one equation for each kind of pattern. So there are two kinds of trees. There are trees which are built by joining a tree 1, a key, a value, and a tree 2. And there is the other kind, which is the empty tree. Okay. So let's do the easy case, I guess. If we're looking up, sorry, I've missed out the parameter, so I've drawn the table. I need a K as well. So this is the key I'm looking for. This is the key I have in the table. This is the key I'm looking for. But actually, it doesn't matter what the key is. If the table is empty, it doesn't matter what the key is because I can't find it. So the answer I return is nothing. There is no key to return. There is no value to return. Otherwise, if I'm looking up a key in a table, what I do next depends. It depends on whether the table is equal, if the keys are equal, if the key is less, or if the key is greater. So there are three cases. So we'll represent those three cases by guards. If k is equal to k prime, I've found the key I'm looking for, then the answer, this key, is the same as this one. Yay! What value do I want? It's this one here. Almost. It is that value, but that value doesn't have the right type. It's a maybe type. So to turn that value into something of type maybe, I need to remember to put just in there. Okay? The other cases are when k is less than k prime. So the key I'm looking for is smaller than the key in the middle. So that means I have to look recursively in the first half of the table, in T1. So in this case, I'm going to recursively look up the key in table T1. And the other case is quite similar. When it's greater than k prime, I'm going to look up k in T2, in the right hand. Okay. Any questions? So, no, it shouldn't be too many surprises. We have a recursive data type. You want to do something interesting with a recursive data type, you're going to need a recursive function. The recursive function will go down into the various parts of the recursive data type, and the two parts of interest are the tree to the left and the tree to the right, the first half of the table and the second half of the table. Any questions? Okay. So we had a look at this example, but how many steps does it take to look up a name in a table with this representation? Well, it depends on the height of the tree, okay? Because in each step of the computation, you go down one level in the tree. So the furthest the most number of steps you have to do is the height of that tree, h. So if the height of the tree is h, then that's the most number of steps that you have to take, right? So that feels very similar to the previous one. If you had a table with n things in, it took roughly n steps. Here I have a table of height h, it takes roughly h steps. So where's the big win? Well, the big win is that for a given height, there can be very many elements in the table. So that's a big win. Because if the table has n entries in it, if there are n names in the table, what is the best height that I can hope for? What is the smallest height that I can hope for? Well, roughly, if I build my table in a stupid way, it might be actually the height and the number of entries might be the same. I might build a table that's like a long chain, basically like a list. That wouldn't be so great. But if I make sure that I balance my table, I have roughly the same number in the left table as I have in the right table, plus or minus 1. If I keep the table balanced, that means that on average, I will have the binary logarithm of n height. Okay? Have you all done trees in your discrete math course? No? So what's the big deal about the logarithm? Why is that a big deal? Well, never mind this table. Let's look at a table of the logarithm. This is the logarithm with base 2, the binary logarithm. So if we have a tree which has n elements, what is the logarithm of n? What is the best case for the height of that tree using this representation? Well, here we have a table, 100,000, there you go, I talked about a million. There's a million, this line here. That means that the height of a tree with a million elements can be as small as 20 if we balance the tree nicely. That's a lot of elements that we can reach in at most 20 steps. That's awesome, right? What does that mean for our algorithm? It means that we can find an element in a table with 1,000 entries in at most 20 steps and at most 20 comparisons in that table. And look how it grows. You can have huge numbers in our table. The number of steps that we require to find things grows very slowly. So this is a big difference to the growth rate of a linear function. A logarithmic function grows much more slowly. So this is a much better time complexity. And that can be very important when we're dealing with big data structures. As our problems get bigger, if the size of our data structures gets bigger, we really have to think about efficient representation. And when I mean bigger, I don't mean the order of hundreds. I'm talking millions and beyond. Okay? So that's a huge win. Any questions? Okay, let's talk about another function. So it's all very well to be able to look up, but sometimes we also need to insert new keys and values into a table. In other words, we need to take a table and build a bigger table, which maybe has one extra entry. Just like we need to be able to take lists and add things onto the lists. We can add something on the front. So we need to be able to insert things into a table. Now, insertion in a list is very efficient. So if we do a lot of insertion but not many lookups, a list can still be very good. Why is that? Well, to add an element to a list, all you have to do is put it on the front. So that's not an order n operation, that's not linear, that's constant. It doesn't matter how big the list is, to add one more element to the list takes a constant amount of time. So that's very fast. We can't do that fast here, but we can still do something in the order of something which is logarithmic. So it's still efficient. So here's the function we want to build. It takes a key and a value. We're not just looking up a key, we're building a new table from the old one, which has an additional key-value pair. So we take a table and we return a new table, which is like the old table, but which has this particular key-value pair inserted into the table. Now we have to make sure we insert this at the right place. We can't just insert it anywhere we like. We have to insert it in a sensible place. If we have a list, we have a table representing this ordered structure where the small things are on the left and the bigger things are on the right, then when we insert something, we have to make sure we put it in the right place. Otherwise, our lookup function won't work. So what that means is that we have a data type, but we have also an important property that every element of the data type must satisfy, a so-called data type invariant. Namely that whenever you build a table, all the elements which are on which come before the one at the root must be smaller, and all the elements which come after must be bigger. That doesn't happen automatically. That's something we're going to have to make sure when we define functions that build tables. And we're also going to probably want to check that with properties using quick check. Okay, so let's take an example. We're inserting the queen into this table. And so the first thing we do is compare with the root. And we say, is the queen bigger or smaller than the root? Does the queen come after or before? Does Q come after or before N? It comes after. So now we compare with the left tree, but the rest of the tree that we're going to build, our answer, will include this node and this half of the tree. So now what we're going to do is modify, we're going to insert into this right-hand subtree. But the rest will remain unchanged. So now we do the same comparison, and we see that Q now is actually bigger, smaller, comes before R in the alphabet. So we're going to insert down here, we make a comparison here, and that means that we're going to end up inserting the queen at the first empty slot to the right of this one. Okay? So you saw how that walked down the tree until we found the place where we were going to insert it, but everything else in the tree remained unchanged. Okay? So let's define that and then take a break. All right, so we're inserting a key and a value into a tree. Let's do the easy case. We have an empty tree. What do we get? We're inserting a key and a value into an empty tree. So we need to represent the table which has exactly one entry. So that is a join of an empty tree on the left, a key and a value in the middle, and an empty tree on the right. So that's our representation of a tree with one element. The other case is where we're joining the left tree, some key prime, value prime, and some right tree. And what we do now depends on what we get when we compare. So if k is less than or equal to, well, let's say, so there's lots of room to do things wrong here. Let's say that if k is equal to k prime, we'll do one thing. K is less than k prime, we'll do something else. And k greater than k prime, we'll do the third thing. I could have written otherwise. So what are we going to do in each of those cases? Well, what are we going to do when the two keys are equal? What's a sensible thing to do? Well, it's kind of like we want to I think a natural thing is to say that the new value that we have should override the old value. So I think a natural choice would be to say that we build the same tree, except that now instead of v prime here, we just have v. Because we're inserting something which is already in the table. So what we'll do is we'll just replace the old value with the new value. Now, whether that's the right thing or not, we maybe can think about what properties that satisfies. If the key is less, then what we're going to do is we're going to insert the key and the value into the left tree. But that's not the answer we're interested in. We're not interested in only the first half of the tree. The rest of the tree should remain the same. In other words, the rest of the tree should be the join of the new left tree, where we've inserted that key value pair, and the same key value at the root, and the right-hand tree, which we left untouched. And in the other case, which is going to be similar to this, maybe not quite similar enough to cut and paste, but I'll do it anyway. That's when we're only doing a function call here, so it's not real cut and paste. It's when we leave the first tree untouched, T1, but we insert into the second tree because we found that the key we're inserting should be over on the right-hand side. So we insert it in the right-hand side and leave the rest of the tree unchanged. So we started with this tree and we modified it to be this tree. The bit that's different is this one here instead of this one here. It even type checks, which is a great opportunity for a break.